Okay, much like related rates, this tends to be a topic where students feel like if they looked back, they would call this one of the tougher ones. You may have already talked with some of your friends who've done this, and they were sort of dreading it. But honestly, the part it all boils down to is much the same as related rates. If you can get past making up your equation, the rest of it generally falls in line fairly easily. The hard part is getting a model together, right? So like in related rates, if you can come up with the equation that models the problem, then the calculus wasn't so bad. Same thing happens in optimization here. So we'll try one together. We'll try quite a few, but again, concentrate on seeing if you can work out the model by yourself, because the calculus skills we're using really just boil down to extrema, which aren't so bad. So in this problem, we have a 12 by 12 box. And in order to make we have a 12 by 12 sheet of paper, and in order to make a box out of it, we're going to fold up the sides by cutting out corners. So this is what it would look like, right? Like my scissors would run across here and chop this out, and then I'd fold everything up. Now, if you use a bit of logic to think about how this problem would work, they have to be the same size or they're not going to meet up, right? You're going to have uneven edges, which means you're kind of wasting some of that paper, right? You could have uneven edges, but why would you do that? You don't need it to be higher than any one side. So that's how we know that these sides are all the same length. That these are little squares that we're cutting out is basically what I'm getting at here. So if we wanted to try to visualize then, what's the volume going to be if we use this model? Well, we're talking about maximizing the volume of a cube. So the volume of a cube is just length times width times height. So that's what we have to dig out of this problem. One other thing to keep in mind when you do these problems is there's generally some sort of application happening, so you shouldn't go beyond the domain. For example, it's possible to make x equal 20, but tell me why it wouldn't make sense to make x equal 20 here. Well, the paper's only 12 inches long, so if you cut 20 inches out of it, you've gone way past the end. You've actually cut the whole side of it off. You won't be able to fold the box, right? So if you were to tell me, what do you think the domain of folding this box up is?
Less than 12.
Less than 12? Okay. And you're just so common sense and practical, you haven't thought of the other one. Greater than 0, right. So our domain here, x has to be a part of round bracket 0, round bracket 12. So here's our considerations. We need to find a volume function, and then we're just going to maximize it. If I was to have already given you the volume function, that's something we've already done. I give you a function, you maximize it, use the extrema. So today we got to practice doing it ourselves. So can anybody come up with a length, width, height formula? Let's just see one piece at a time. Can somebody give me a length formula? Pardon me? 12 squared, okay. How did you get 12 squared? Right, so Leo's just realized that if you make them both 12s, you haven't cut corners out for a box, right? So what we have to do is, if I've taken x out of this side and x out of this side, what's left over here is going to be 12 minus 2 of those x's, right? So if you picture this box, 12 minus 2x is each of the dimensions for length and width. How tall is the box going to be? Yeah, you have to visualize it. When you fold this up, x is going to be the height. So if I gave you a function, it would look like this. 12 minus 2x, 12 minus 2x, and then the height is x. So I'll rewrite this as my volume function for x is this. And I probably will want to go, it might be more convenient to do something like x times 12 minus 2x all squared. But at this point, now that we've gone this far together, I want you to find out the answer. What's the biggest volume you can make out of that piece of paper if that's how you build it? Right? So see if you can maximize it and find the answer to this. Okay, so I'm going to try and catch up here. Maybe I'll expand it here just so that we can, it's still quite early in the morning here. Maybe this will be the way to go. I'd have 144 minus 24x plus 4x squared times x. And that's going to be, let's see here, 4x cubes minus 24x squareds and 144 x's. So yeah, that's certainly fairly easy to do. That way I have a simple derivative. So my derivative is going to be, let me just change this thickness here for a sec. Okay, so the derivative for the volume is 12x squared minus 48x plus 144. And I can take a 12 out of this, so I will. This would be 12x squared minus 4x plus 12. And I believe this should factor. Let's see here. And I've just realized then that there is a, because it's supposed to factor here when I thought this one up, that was the original problem. My apologies, that should be a 48. Because it would have been 24 and another 24. So that's going to change how this factors. So this is, what do we say here, 96. And that'll be an 8 here. There we go. Now it's going to factor. So this should be x minus 6, x minus 2. Okay. So tell me something now about what do you think happens at x equals 6? Why is that not something we should consider here? Use some common sense. Don't dig too deeply into the calculus of this. Yeah, if you cut at 6, because you have to take 6 off of each side, that means you'd actually cut all the way through. So that means our domain here, be careful, it's actually, you would figure this out when you tried to find your answer, but we should really stop at 6, because if we go past 6, we've cut the whole end off the box. Originally we thought it was 12, but we forgot there were 2 sides to the box we cut. Again, if you forgot that you're out of the domain, if you put this in, your volume formula here, these pieces are going to equal 0. You're going to get a volume that tells you there is no volume. So anyways, you get away with not being in the right domain, but that means we only have one critical point at x equals 2. So at x equals 2 then, this could be a minimum or a maximum. What do you think? It's probably a minimum? Not a minimum. Okay, why do we need to say probably? I know it's early, but you should be able to give me a reason why or why not. There's several ways to determine this, so think. Okay, so if 6 is a minimum, then it's not necessarily true that 2 also has to be a maximum, because it could keep going down from, all we know, we just said that at 6 it's equal to 0, right? We didn't say that 6 was, the end of it a minimum, but you're probably right in this case. But how could you determine this quickly? You have 2 ways of doing it. Jog my memory. What could we do? Second derivative test? What's the other technique we could do here? The number line, which we call first derivative test. So there's 2 ways to do it, and it's really convenient that they're numbered as well, the first derivative test or the second derivative test, right? So in this case, if I had to pick one, I'm going to pick the first derivative test. Now I know you don't normally like number lines, but for me, I already know what the number lines are because I've already factored it and I have my pieces. So for this number line, everything's ready to go. There's nothing wrong with finding the second derivative and testing it. That'll work too, but it's your own personal preference. So either way that you did it, Again, for me, I would have x minus 6, x minus 2. There's a 2, there's a 6. Negative, negative, positive. So this is a positive, this is a negative, and this is a positive. But remember, that doesn't really exist in this problem because the box is gone after that point. So 2 is a what? Minimum or maximum? It's a maximum. It's increasing to decreasing. That means it has to be a maximum here. So at x equals 2, that's the largest dimension or value we could use. So if x equals 2, then this is going to be equal to, what's that, 8. So the largest dimensions would be 2 by 8 by 8. Okay. Now, the other thing to keep in mind, sometimes when you get tripped up in optimization, it's not that you can't come up with the right equation. The problem tends to be that your equation you get has more than one variable. You always have to have one variable. We're only doing calculus of a single variable here. I know there's implicit derivatives and yada, yada, yada. But when we do these optimization problems, your goal should be to try and get it down to one variable. So well, let's talk about this one here. Which points on this parabola are closest to 0, 2? So this is kind of a strange problem. Let me give you some context. That dot is the Earth. This arc, let's call this a comet or an asteroid or the moon, whatever. It's something passing by us. So you're working at NASA and you're like, oh, good thing Mr. Joyce taught me all that calculus. Let's find out when we can meet up with this asteroid. If you told NASA, let's launch over to here, they're going to say, thank you for your service. It's been nice knowing you. Go have a job somewhere else. Obviously, the amount of effort it takes, we want to try and get as close as possible. This would be a better guess, but it might not be the right one. Somewhere in here, maybe this is the shortest path that we can find. We come closest to that thing skirting past us. So that's what we want to know is, what point is it where we're going to be closest to that dot? So how do you find out how far away you are from something? With a ruler. Perfectly acceptable answer, yes. Was not expecting that kind of practicality, common sense. You need a very long ruler if you're working for NASA. What do you think? How do you know how far away you are from something? For example, if I was like this, does that jog your memory? If I want to know how far that black dot is to the purple dot, I could tell you how far it is now. Anybody know how far it is to get from here to here?
1 squared plus 2 squared.
Which is also known as?
Root c squared.
Okay. Root 5. Yeah. Okay, so Jem just said that it's 2 here, 1 here, so 2 squared plus 1 squared is root 5. Distance. We're talking about distance, so the distance formula is our tool. So if you've forgotten how that works, the distance is root x2 minus x1 squared. Just a second here. Sorry, your question was? Which one? This here? Oh, okay, yeah, so it's a little smaller than the tick marks here. It's a half and 1. So yeah, the math is a little more difficult here. It's going to be 1, and that's a half. 1 squared plus a half.
1 and 1. That's 1 and 1.
Oh, God. You'd think I could count to 1 by now, right? So that would be root 2. Okay. So here's our distance formula then that we're going to use. But it says very specifically that it's not talking about any old point. We're talking about the point 0, 2. So how could I update my distance formula? Pardon me? Yeah, we have a value here for x and y. It's got to be, that point is fixed, 0, 2. So in our problem, we're not interested in just any old values. It has to be between those. Now, so far so good. However, I don't want to deal with x's and y's. I just want x's in this when I'm going to maximize it. So can anybody think of a clever way? You've had your coffee this morning, I see. No? Okay. Right, so we have this relationship here. That means we don't need to use y. We can just say this is, I'll call that x squared, 4 minus x squared minus 2. So if I update this distance formula, this piece here is going to be 2 minus x squared, all squared. So this will be 4 minus 4x squared plus x to the 4. So I'll collect these like terms up a little bit here. Okay. So I really wish this would factor nicely or simplify, but unfortunately it doesn't. So at this point we'd have to take a derivative and start work there. So we're going to try that. Can anybody think of a strategy before we get going, or are we just going to jump in? It's Monday, it's 9 a.m., right? Let's just go for it. Okay. So I'm going to have 1 over 2 root x to the 4 minus 3x squared plus 4 times 4x cubed minus 6x. And then let's take out, might as well take out this common factor here. I have 2x, and that'll be 2x squareds minus 3. So those come out. And I can see some critical points already. So what numbers would I need to check here? Any ideas where we could pull out some critical points? Okay, there's one. Good. If you solve this equation here, 2x squared minus 3, you're going to have 2x squared equals 3. So that means x squared is 3 over 2. So x should be plus or minus root 3 over 2. This pen is horribly sticky today. Okay, so root 3 over 2 and negative root 3 over 2. Any ideas there about the bottom? Plus or minus root 2? How did you get that?
Well, I could, the bottom was, never mind, sorry.
That could perfectly be valid. Can you explain how you did that?
Because I looked back at when it was like, oh my god.
Yeah, it'll do that to you. Let me help you out here a bit. This is one of those things where it helps to have some practice, because You missed something very important here if you haven't had somebody help you out with it. What would happen, think about it, if we made the bottom divide by 0? What would that say about the original problem? Okay, we're thinking too hard, I guess. Look right here. If we made this equal to 0, what would that say about the original problem? This is a derivative, right? So we make it equal to 0 where it's undefined, and what will we be finding out? We go to all this effort, and it would tell us what?
Sharp turn.
Well, it wouldn't be differentiable there, but I'm trying to get at, is that useful information to us? Where have you seen this before? Look at it. Look familiar? The distance would have to equal 0. So we just would have wasted time because that doesn't happen here. So if it doesn't happen, we know it doesn't equal 0. That would mean that asteroid just crushed us. So we hope that's not the case. But anyways, the point is, you're looking for something that didn't happen, because if it does happen, the distance must equal 0. Okay? So these are my only critical points that I could use. 0, root 3 over 2, and negative root 3 over 2. Now right away I can tell you that 0 is not a critical point because it's really easy to see the distance there as long as I count properly this time. That distance is 2 and root 2 is already smaller. I just shown you one where it's smaller, so I know that can't be the one I'm looking for. Now why do you think that root 3 over 2 and negative root 3 over 2 show up? Like, are there really two answers there? Why is that? It's symmetrical, right? You look at that problem, you'd expect the same answer on either side. So these would in fact be either location for us, right? So you could say, well, we can aim for the first one, and if we miss it, then maybe we can chase it over to here, right? If you did this last one and you missed it, then you have no other option, right? But either of those points will find the minimum distance for us. Now, the reason I also wanted to show you distance was not just to highlight the fact that you don't need to look for where it's divided by 0, but there's another thing that comes out of that we can also use some common sense and help us on distance problems. So if we're trying to do a distance problem, what's going to happen when we do this is we have this really awful square root. It makes life difficult. But what if we considered this? Oops, sorry. What if instead we thought of the distance squared? This is, after all, what Pythagoras' theorem says. What if I considered this one instead? Would you believe me if I told you, and don't just say yeah because you're my teacher, that I maximize the distance squared will also maximize the distance? Or sorry, minimize, right? We're trying to minimize. Well, why wouldn't you? If I find the smallest number that comes out of the distance squared, and then I square root it, did it just all of a sudden become the biggest number? No. If you follow this one through, and there are some bigger reasons in the background happening, we can maximize distance squared, which means we would just be maximizing this function in here. Okay? We wouldn't deal with the square root. Distance squared is x to the 4 minus 3x squared plus 4. Watch what happens when I take the derivative. Where did you see that?
Over there.
It's over here, right? It's from the chain rule. That's the only part of the derivative that gave us our answers, was the one that we used in the chain rule, because the one on the bottom doesn't give us an answer if we divide by 0, because the distance has to be 0. So the only place that I'm going to find that maximum is from the chain rule, which means if I remove the square root, there's no chain rule to do anymore. I'm back where I started. I'd be maximizing this function, dealing with 12x, or sorry, that is the one. That would be 2x times, what was it? 2x squared minus 3. So I would get x equals 0 and plus or minus root 3 over 2, just like we did the last time. So that's a valid technique for you to use. When you run across distance, you can make life a lot easier if you just maximize distance squared. Right? If I told you the shortest distance to my house squared was 9, then what do you think the shortest distance to my house would be? Did I say that too fast? Yeah. If the shortest distance to my house squared is 9, then what's the shortest distance to my house?
3.
Genius. Yeah. Okay? Okay, now this is one I always think of in practicality terms. I don't understand why I mean, maybe I'm too type A in my personality, right? Maybe I'm a little too much like that Sheldon from The Big Bang. Because for me, when I read this and I try this question, every time I do it, I cannot understand why Coke and Pepsi waste so much aluminum on their pop cans. But maybe we can figure it out, right? I mean, if I told you that I was going to make a 1 liter, well, that's quite a big can, right? But anyways, you could do the same thing if we were dealing with a 355 milliliter, whatever it was. But, you know, you picture all the different cans that are on the shelf. You know, if you're drinking out of a pop can and it looked like a tuna can, you know what I mean? Like a tuna can, like short but very wide, that would be awkward, right? Yeah? So at some point, Coke and Pepsi are going to go, well, even though it would save us, you know, whatever many millions of dollars, no one's going to want to buy these silly looking cans, so we better just, you know, use a different idea. Or on vice versa, if it was very tall and skinny, like if I said, oh, I can save this company millions of dollars, all we need to do is make a 3-foot tall can that's 1 centimeter wide, right? Nobody's going to want to carry that around. So at some point, practicality has to kick in, and there has to be some aesthetics that, you know, help us sell our product. But let's live in this perfect type A world where everything is exactly optimized, and let's see how far off we really are. So we're going to take the material to build a pop can, and we're going to try and minimize it. So what I'm telling you is, you got to build a 1 liter pop can. You can do it with as, you know, much or as little as material as you want, but your goal is to minimize the amount of material you use. So it helps to have some perspective on what we're doing here. This is what a pop can looks like if you unroll it. Right, the middle piece is actually a rectangle. It just unravels the pop can. Right, it used to be a cylinder, and then it unravels into a rectangle. And then the 2 caps that are on the end of it are those 2 circles at the top and bottom. So that's how I can get this this formula here, that the surface area. There's a well, each one of these here has an area of pi r squared. Pi r squared. So there's actually an r missing up there. And if you think about what are the dimensions of this can, the can is some height. Its width is the same as unrolling that circle, because if they don't match up, the circle won't close it, right? So that means the circumference of this circle is 2 pi r. That's how wide the can is if we unroll it into a rectangle. So that's the area of the square here and the 2 end caps. So if you're using those aluminum sheets, that's how much area you need to use to build a pop can. Now the other thing we know is we're making a 1 liter can. So the volume of the can, pi r squared h, has to be equal to 1,000. So under these constraints, we're going to now try to minimize the surface area. We want the least amount of surface area to make a 1 liter can. Okay, so we have this surface area function. Can anybody tell me what's wrong with it right now? 2 variables. But that's why I gave you some extra information to help us figure this out. Could we use the other one to help us out?
Yes. Actually, go 1,000 over pi r squared h.
Good. You're going to make a good pop can designer one day, Leo. 1,000 over pi r squared. Or maybe it's tuna cans. I don't know. Whatever you see, a cylindrical can. And it's going to bug you now, because next time you go grocery shopping, I guarantee you're going to look at those things and you're going to... Anyway. So the height is 1,000 over pi r squared, which means I can update my surface area formula just in terms of the radius here. So then that means I'm going to be left with 2,000 on top and an R on the bottom. Because that R will be gone, the squared. There. Okay, so I've done a lot of the legwork. Again, the hard part for you is going to be trying to get your models to line up. Once we're there and we have a model, this is where I expect you're able to do your own work now. So try this one. Can you find what's the optimal radius? What radius will use the least amount of surface area, right? Go save these companies millions of dollars. Yep.
What is the surface area formula again? 2 pi square r or 2 pi r?
Pi r squared. That was meant to be like that. I don't. The r was out of there. It was from this picture here, right? Pi r squared is those two end circles, so it should have been 2 pi r squared. So I think I have a critical point here. There's one that you can clearly see on the bottom. You can't divide by 0, so radius 0 would be a critical point. However, you don't have a pop can if you do that, right? So we wouldn't consider it. But I can look for a critical point elsewhere. What I decided to do was factor out that denominator, or you could make a common denominators. You could also just solve the equation 4 pi r equals 2,000 over r squared, because if that's true, it equals 0, this expression here. So there's many ways to get there, but when you do, I believe this is the critical point you walk out on, is 500 over pi's cube root. So I don't know how funny looking that is, but let's just see what kind of radius I would have if I did that. So I have a radius which is going to be about 5.42, and then I can figure out what the height would be here if I square it, times it by pi, and then use that in here. So I get 10.84. So the height would be 10.84, and the radius would be 5.42. Would you drink out of that can? How could you picture it? Could you explain to some? Look at those proportions. What could you say? The radius is what to the height? Half the height. So another way you could probably picture it easier is you could say that the diameter would have to equal the height, right? Because 2 radius, then I'm equal to the height. So that would be a can where it's as tall as it is wide. So it'd be, I don't know, a little, I guess we're talking about maybe a soup can here, or I'm not sure. But anyways, I don't know why they don't do that. I don't think it's that weird to drink from a can that would be as tall as it is wide. But anyway, that's the most efficient way to do it. So you notice that pattern? That's one thing, again, that if you were doing this in industry or just out of curiosity, you would want to know, does that pattern always happen? Let me try something other than 1,000 milliliters or 1 liter. let's see if it happens again. Is it always a ratio of 1 to 1, same diameter as height? In this case, I'll spoil it. The answer is yes. Yeah, if you do a can, the best can you can make will have a diameter of a ratio of 1 to 1 for the diameter and the height. All right, so last thing we'll take a look at here. This is a calculator problem for sure, so definitely pull out your graphing calculators to help you through this one. Think about this like, I guess we'll call this the desert island math. You know, the captain pulls up on his ship and he says, I have 4 feet of wire. If you can build me the maximum amount of area, you can come on the boat and leave the island. So here's the thing you have to do. You have 4 feet of wire. You get to use a circle or a square, or both, whatever you want. But you have to make a maximum area out of it. So how could you maximize the area given 4 feet of wire? Okay. Think about, what is your formula going to look like for the area of this figure? Think about, if you can get there, maximizing it, and check your critical points and see what will come out. Okay, I want to see how you do with this one on your own. Start with the model. What does your model look like for area on this? Okay, so I did see quite a few people had some success finding the area. So if this is a square, I know that they're all the same side lengths. So, oops. And then this circle has a radius r. Then that's what my area function is going to look like. That's what I have to try to maximize. Now, the only problem is I've got 2 variables right now. So it tells me that 4 feet of wire is what I have. So those variables have to obey this rule as well. The circumference of the circle is 2 pi r, plus the 4 sides of the square have to add up to those 4 things I had. Okay. So then let's come up with, we'll solve for one of these here. Let's see. Solve for r? Okay. So 4 minus 4s equals 2 pi r. 4 minus 4s over 2 pi is r. So I could call this r equals 2 minus 2s over, oops, that's not a 2, over pi. Okay, so my area then becomes, area is pi 2 minus 2s over pi, all squared, plus s squared. Okay, so let's expand out and see what we have here. This will be pi, and I'm going to have 4 minus 8s plus 4s squared, and it'll be all over pi squared. So that pi would be out, and so would that exponent, which would leave me with an area formula that says 4 minus 8s plus 4s squared over pi plus s squared. So that gives me an area just in terms of the square. It should be the same, well, it won't be the same formula, but it should give you the same answer if you did it in terms of the radius. That would also be fine if that's the way you chose to do it. But now that we're here, we're going to find the derivative, and as I mentioned, we're going to use the calculator to help us find this point. So let's go and find the derivative. Okay, this piece here is just a constant. So this pi, you could think about it like 1 over pi times 4 minus 8s plus 4s squared. So since it's a constant, I don't need to, geez, I don't know why it's so bad at writing today. Since it's a constant, I don't need to worry about it in my derivative. It's just going to be these pieces here. It'll be 1 over pi, and 4 is gone, so negative 8 plus 8s plus 2s here. Oh, I don't know why, but the geek in me just has to do it. You could just put it in your calculator now and go, but I think I'm going to have to give this a try and see. Can't let it beat me. Negative 8 plus 8s. Okay, yeah, and I probably don't want to. Yeah, I don't want to. You don't need to factor that, but let's see if I can solve that equation here. I'll have. All I'd be worried about is the top. So I'd be dealing with 2 pi s plus 8s minus 8 equals 0. So I can take the s out of here. So s is 8 over 2 pi plus 8. So that would be the side length I'd be looking for on this square. And I'll fix that 8. It's not very easy to read. 8 over 2 pi plus 8. So I have one critical number here. I can use that critical number to test out if it's going to give me the maximum area. So the extreme value theorem is what we're doing all the way through this. Where do I have to look other than my critical points? The endpoints. So what would be the endpoints of this situation? 0 and 1, right? Because at 1 I would have just a square, and at 0 I would have just a circle. So my endpoints are going to be s equals 0, and you should tell yourself this is a circle only, and s equals 1, which is a square only. Because if s equals 1, there's no material left to build a square or circle. So let's find out what a at 0 is, a at 1, and a at 8 over 2 pi plus 8. Okay, so just a reminder, the function that I'm trying to maximize is this one right here. So it is pi. Oh, sorry, that's we simplified it to this one down here. We simplified it to 4 minus 8x plus 4x squared divided by pi plus x squared. So that's what I'm trying to maximize, and I'm using my extreme value theorem to find out where that maximum is. It's either the critical point or it happens at the endpoints. So the reason I wanted this was so I could be lazy and not have to keep typing that in. So if I use the table method, I have to get it to ask me the independent variable. And the table, we want to check it out at 0, at 1. Those are the endpoints. And the other value here, which is 8 over 2 pi plus 8. Okay, so what do you see? Yeah, this might be surprising to you, but this is actually true. If you were to do this, we actually found a minimum there at 5, 6. That's the worst way to make the area with that value I just found. But at 0, when I just have a circle, that actually gave me the most area. So a circle only is the answer to this little riddle. So you get to get on the boat and everything's good. Anyway, but just your nerdy fact of the day. And if I give you any amount of string or whatever it is, a circle is always the way to go. Circle is always the biggest area for any kind of length you have. This would be the start of kind of a proof. It'd be like, what other shapes could you make than a circle, right? Well, why would the square is clearly not a good strategy, because as soon as I start adding a square, I start losing out on area. Circle by itself trumps square, or circle and square, right? Anyways, but it is the largest area you'll get for a 2D figure.